Hi, welcome to the ninth week of the course. This week we'll continue with our development for compression. And before I begin lectures for this week, let me quickly review what we saw about compression last week. So we were looking at now a few different formulations of compression for compression, and the first one is that of fixed length codes, and that's something that we have seen earlier in this course, fixed length source codes. And corresponding to this, we had defined this fundamental quantity L epsilon. Maybe I should use L epsilon x. This is the minimum length of a fixed length code. So minimum number of bits, fixed length code used to store x and recover it exactly with probability of error less than epsilon. So that's the quantity L epsilon x, and we have spent some lectures to understand why this quantity is close to entropy of x. Okay. Beginning last week, we started looking at the perhaps more practically relevant for some application setting of variable length codes. Okay. So these are the codes. These are the source codes where the encoder takes a source symbol from the set x and maps it not necessarily to a binary sequence of fixed length, but to a binary sequence of an arbitrary but finite length. So if you have a symbol x, this mapping will take it to ex, and this ex will be a binary sequence. So this ex, you can think of some examples. It will be a sequence like this, or some other sequence. Okay, so basically it can be any binary sequence. So these are variable length codes where different code words corresponding to different x's can be of different length. And for this setting, we define the quantity L epsilon bar x. This bar denotes averaging, just like mean. I'm just using a similar notation. This is the minimum expected length. Minimum of expected length. How do you write expected length? It's expected value. So summation over x px ex. This is my notation for length of the binary sequence ex. So expected length of the sequence minimum over all x, such that, so you take minimum over all encoders and decoder pair D, which we can call all source codes, such that the probability of error. Now, how do we define probability of error? We saw this last time. That's the probability that if you decode E of x, that does not coincide with x, and you want this to be less than equal to epsilon. This is this parameter epsilon here. Okay, so the only difference between this quantity and the fixed length quantity here is that this variable length quantity allows code words of different lengths, and you are looking at the minimum average length, whereas this quantity will look at the minimum worst case length. So we started looking at this quantity L epsilon bar x, and we showed a result. We showed that this quantity actually is no less than entropy of x minus something which can depend on epsilon. Okay, we allowed that dependence, but it cannot depend on epsilon too severely. So what we showed was that this is, I'll just put an approximate sign here so that we just get the gist of the result. Epsilon log cardinality of x minus another log h epsilon, hx, I think. Yeah. So these terms are all much smaller when compared with this. In fact, as I pointed out, this dependence can also be improved, but we will not worry about that because we assume that epsilon is very small. Okay, so if you're looking for such mappings, then L bar epsilon x, the minimum average length, cannot be much smaller than hx. So this week we'll continue our discussion on compression, and what this result here, this theorem that we proved, provides us is a benchmark to strive for. So we want to design codes which roughly attain this entropy of x as average length. Okay. Also note that we have not imposed any extra structure on this code. We're just saying take any encoder decoder pair such that their probability of error is less than or equal to epsilon. In fact, in practice, we would like to impose some more structure. We would like to impose a structure of so-called prefix-free codes. Okay. And also often in practice, we may not want this epsilon to be there. We just want epsilon equal to 0. So epsilon equal to 0. So this can be called as error-free. Okay. So even in these settings, we can actually study this problem, and I'll describe what prefix-free codes are, and I'll discuss how to attain this bound for epsilon equal to 0. So that's what we will see this week. I hope you're having fun in the course. See you in the next lecture.